The site to be analyzed is the Heriot-Watt University situated in the International Academic City in Dubai, UAE. The site receives unhindered sunlight for majority of the year and sparse rainfall spread out during the winter season, with a few spells of heavy showers. The region receives an average of 25 mm of rainfall during February, which is the wettest month recorded in this region. Summers have an average of 40 to 41 degrees Celsius high and an average of 30 to 32 degrees Celsius low. The winters have an average of 23 degrees Celsius high and 12 to 14 degrees Celsius low. The site receives sunlight over the eastern facade for majority of the day, which is the side facing the main entrance of the building. The region is very hot and humid for majority of the year, with an average relative humidity of about 50 to 60%. The electricity is provided directly from Dewa. Thus, there aren't any existing energy sources on site. This video will be exploring the prospect of energy generation through solar, wind, kinetic, hydro, and geothermal means in the provided site.
The energy consumption analysis of the Heriot-Watt building shows us the various elements that require energy in an institutional and accommodation building. Up to 50% of the total consumed energy is dedicated to the air conditioning system. The lighting service also requires high energy. Other services which do not consume as much energy are the fire safety system, water management, electrical and lab equipments, and the waste management system. The electricity consumption measured in kilowatt hour for the years 2012 and 2013 are seen in these graphs. The loads are plotted against months. A variation in the loads is observed, possibly due to the changing climatic conditions of Dubai and the working hours of the university over the year. Next, we see a higher energy peak in September 2013. This had occurred because of the initiation of Phase 2, the accommodation building. The peak leads us to believe that the energy consumption can rise up to 5,000 megawatt hour in the following years, with the increasing number of occupants and the introduction of latest laboratory technologies and equipment.
Solar energy. Rooftop solar PV is becoming economically attractive in Dubai, where the price of electricity is relatively high compared to most GCC countries. Thus, the current slab electricity tariff makes self-consumption of distributed power generation more likely now and into the future, as solar install costs are continuing to fall and the cost of electricity from fossil power generation likely rises. By 2020, Dubai had planned to supply only 1% of electricity from renewable sources and 5% by 2030. However, the targets were increased in early 2015 to 7% and 15% respectively due to exceptionally low utility scale solar PV tariff established in the Emirate. PV is surely one of the main pillars of its plan for meeting these renewable energy targets for 2020 and 2030. Dubai has established a net metering program too to encourage this, called Shams Dubai, which encourages tenants and building owners to install PV panels to generate electricity. DEWA connects the individual systems to network so as to take up the surplus power generated, if any, encouraging this throughout the country and even diversifying their energy mix. According to Dubai's issued resolution in 2014, a consumer can generate more electricity than consumed, and the surplus energy is carried forward as credit to the following bill with no time or quantity restrictions. And this can be an advantage of our design here in case of any surplus availability. A solar PV system basically consists of a semiconductor material that converts solar energy from the sun to the electricity. The amount of sunlight is the main deciding factor, which works out well because of Dubai's high irradiance values here. A typical off-grid PV system includes solar panels, charge controller, inverter, and a battery. In such an off-grid system, the generated electricity is stored in batteries and then further distributed. But here, because of UAE's conditions, a grid-connected system is preferred, which requires no batteries. This table here shows various installation configurations and corresponding costs from which the standard panel rating was found to be about 156.25 watt per meter square, and the capital cost of it being $2.4 per watt for a 200 kilowatt system, according to which the payback period was calculated. These standard values were obtained by a research conducted by Stephen Griffiths and Robin Mills. The payback period calculation here shows that the expense to set up a PV system using maximum available rooftop area in this Heriot-Watt building comes up to about 2.25 million US dollars, that is above 8 million dirhams, that can supply only about 1711 megawatt hours annually. The payback period here is about 10 years. So in conclusion, solar energy can be a viable option because of the system's lifetime being about 20 years and producing about 35% of the electricity annually. However, these numbers may change because of varying operational costs in each year and increase in electricity demands that can happen due to increase in students or other factors as mentioned. The affordability of initial cost of the university is also a factor.
Wind turbines. Electricity generation is made possible by the use of wind. Wind is a renewable energy source used to rotate the rotors of the turbine. The mechanical energy generated by the rotors is transferred to the generator. The generator then converts the mechanical energy to usable electrical energy. Restricting ourselves to finding a local company in the UAE, Merkur German Renewable Technology is a supplier of wind turbines located in Dubai. The company provides wind turbines for microgeneration. The average annual wind of the region is 7 meters per second. This will affect the efficiency of the wind turbine's output. The initial cost of the turbine is calculated based on its output. Each watt output for a wind turbine costs around $1.4. Since the total output of the wind turbine is 3,000 watts, the total initial cost of the unit will be $4,200. The maintenance and operation cost for a year is about 5% of the initial cost. The income generated each year is multiplied by the selling tariff, which is $0.035 per kilowatt hour. This is then multiplied with the output and its efficiency. The income generated annually is $210. The total life cycle income from the wind turbine is $9,200. Subtracting the total income from the operation and investment cost, the net profit accounts for only $800 or 3,000 dirhams for the local currency. This is a very small amount which resulted because of the region's wind decreasing the wind turbine's output.
Hydropower is the generation of power by the use of water. Water at different heights, flow are used for this purpose. Small hydropower plants are more likely to be run off river facilities than are large hydropower plants. Since Heriot-Watt University is situated in an academic city, which is not even remotely close to a water body, prospects of utilizing seawater is very less. If a reservoir can be built under the authority of the government, a setup can be made to produce power by using the water's potential energy. But since the area hasn't much developed, the idea of a reservoir is not a feasible one. Possible solution for hydropower could be using lucid power pipes. These are pipes that are fitted with turbines that are in turn fitted with motors that generate electricity. But since the university has already been built with water supply, it is not feasible to remove the existing pipes and replace them with lucid energy pipes.
The alternative hydropower option chosen is the steam engine option, where the steam engine machine operates by the cycle of channeling water into the pipeline and downstream passing through turbines and returning it to the water source. These engines actuate from a head height of 3 meters. The engine used for the study was LH100. The design requires low head and a high water flow rate. It operates best between the head dimension of 1 meter to 3 meter with a minimum flow rate of 100 gallons per meter. The water passes through guide vans, which in hand operates the propeller connected to the generator. The water is returned into the originating water resource by passing through draft tube. The possible technology was rejected as upon calculation it was found that the output would result very low. The insulation of jet engines would result in excessive refurbishment and causing it to be too expensive for the scenario. Geothermal energy is obtained from heat under Earth's surface near aquifers. There are two types of geothermal resources, the low enthalpy geothermal resource and the high enthalpy geothermal resource. The most viable within the region is the low enthalpy resource. In the possible technology, the binary power plant transformer principle can be implied. This consists of a system comprising of a working fluid, which is an organic compound consisting of a low boiling point. This possible technology was rejected as it might cause space restraints in relation to construction and cause disturbance to the users within the university. Biogas renewable energy. Organic biodegradable content such as waste material and sewage is treated within digester. The possible technology thought of was an off-grid system which consists of a digestive tank underground where the waste generated within the building is piped underground to the digester and is held in the gas holder furnace. This possible technology has been rejected since it might only result in being 20 to 30% efficient. Energy is consumed in order to convert this mechanical energy into electrical energy, making it less sustainable, and this might even lead to bad odor.
Kinetic energy, a lesser-known source of renewable energy, can be successfully employed through the use of a recently advancing product called as the Pavement tiles. Pavement tiles are tiles that convert human footsteps into electrical energy. This has been used in various parts of the world and is expected to be one of the cheapest energy sources in the coming years. Pavement tiles could be placed in the university where movement is frequently observed. Play courts, pathways to the food court, and smoking area are the few areas where movement is seen all the time. Energy can be stored in batteries or directly be fed into systems that utilize the tile's energy.
While installing renewable technologies is an optimal solution, there are some limitations posed by the university. It is an ever-expanding and continuously changing building. The main limitation faced is the space constraint. After analyzing geothermal, wind, kinetic, solar, and hydro energy sources, it can be concluded that a setup of a new renewable technology requires a large initial investment, design modifications, and a construction process that may hinder the working of the university. However, using kinetic energy through installing pavement tiles seems to be the most viable option due to its ease of installation and the kind of space available. Along with this, it is of very high importance that students, staff, and faculty members employ sustainable practices in their daily activities, such as switching off lights and AC systems while leaving the classroom or the dorm rooms, switching off running taps when not required, recycling paper, plastic, and glass, attaching a faucet aerator on taps, and using appliances that are energy rated. Such options are often overlooked by users despite of how effective they are in reducing the energy consumption of the building.
I hope this video inspires you to step up your sustainability game, and this energy audit concludes here. This energy audit was carried out by the students of Heriot-Watt University Dubai campus for the same building and under the guidance of Dr. Jun Han for the course D19 EB Energy and Buildings. No energy was wasted during the making of this video.